Another possibility, however, is that these gravitational waves were produced in the early universe, so fractions of a second after the Big Bang.
Welcome to Chelonia Podcast, a podcast about the use of scientific discoveries and of technology applications. We provide the best information on projects participated by Chelonia and many more. My name is Gabriella Bernardi, I'm a science journalist, and in today's episode of the second season, we talk about NANOGrav Collaboration, the Big Bang and Gravitational waves with Dr. Andrea Mitridate, researcher at DESY. Nice to meet you. And would you please briefly introduce yourself and tell us what are gravitational waves?
Hi, Gabriella. First of all, thank you so much for inviting me. It's really a great pleasure to be here. So my name is Andrea Mitridate, and I'm a particle physicist from Florence in Italy. Which is also where I did my undergrad studies before moving to Scuola Normale in Pisa. So after these 28 years living along the Arno River, I decided to move all the way to California, Caltech, which is the California Institute of Technology, where, among other things, I got interested into gravitational waves, and more specifically, how we can use them to study the cosmology of the early universe and particle physics. And because of this interest, I joined the NANOGrav Collaboration, which is a collaboration of several scientists which are trying to detect low-frequency gravitational waves. And more recently, I became co-chair of the working group of this collaboration, which is trying to use a possible detection of gravitational waves to study the early universe, and I'm continuing to do so now that I'm at DESY in Germany. So, I already mentioned gravitational waves, so maybe let's discuss a bit more what is a gravitational wave. So, very concisely, a gravitational wave is a ripple in the fabric of space-time, which is propagating at the speed of light. So this is a very concise explanation. If we want to understand a bit more what is a gravitational wave, I think we need to understand the differences between Einstein's theory of gravity and the more traditional Newtonian theory of gravity. Well, actually, in Newtonian theory, gravity is a force. So if you have two objects with some mass, they will attract each other with a force which is proportional to their masses. In Einstein theory, every object which has a mass will curve space-time, and this curvature is gravity. This curvature, for example, is what will dictate the motion of planets around the sun. So there is no force pulling the planets around, but it's the curvature of space-time induced by the mass of the sun, which is dictating the motions of the planet. Now, a static object, so an object which is static in space and time, which is not moving, will produce a perturbation of space-time, which is also static. But if you have an object which is moving, more specifically it's accelerating, this will produce a perturbation of space-time which will propagate. So if you think, for example, to a lake, and you throw a stone in the lake, this will produce perturbation, a ripple on the surface of the lake, which will propagate. And similarly, an accelerating object will produce a perturbation of space-time, which will propagate. And this perturbation of space-time, which propagates at the speed of light, is what we call a gravitational wave. And in principle, anything which has a mass and it's moving will produce a gravitational wave. So if I will start running around this room, I will also produce a gravitational wave. Of course, this will be too weak to be detectable by any conceivable experiment. So if you want to find gravitational waves which are loud enough to be detectable by experiments, you need to go after the biggest and more dense objects that we know of. And typically these are black holes, more specifically usually binaries of black holes, so pairs of black holes orbiting around each other. This kind of system can produce gravitational waves which are so strong that hopefully they will be able to leave a detectable signal in our experiments.
Could you please explain what NANOGrav Collaboration is?
NANOGrav is what we call a pulsar timing array. And it's not the only one, right? NANOGrav is the one based in North America, but there are several other ones operating in Europe, China, India, Australia, South Africa. So what is a pulsar timing array, or PTA in short? So the idea behind this kind of experiments is to use a collection of pulsars to essentially build a galaxy-sized detector for gravitational waves. A pulsar is a rotating neutron star. So it's a neutron star which is rotating around an axis, which we usually call the spin axis, but it's also emitting radio waves out of its magnetic poles. And as the pulsar rotates, it will appear to us as a lighthouse. We will receive a flash of these radio waves every time the pulsar completes a full rotation. And these objects rotate with such an amazing precision over long time scales that we are able to predict all the future time of arrivals of this flash of radiation with an accuracy of nanosecond, which is amazing. And there are a bunch of these pulsars that we can monitor in time in the nearby galaxy. And by observing all these pulsars and monitoring the arrival time of the flash of radiation that they emit, we get what we call a pulsar timing array. Now, if we go back to what we were discussing just a few minutes ago, we say that a gravitational wave is a perturbation in the fabric of space-time. This gravitational wave will perturb distances between objects. So if you imagine that there is one of these gravitational waves going through our galaxy, what the gravitational wave will do is to perturb the distance between these objects, the pulsars, and the Earth. And what will this gravitational wave do is that will cause the flash of radiation, which is emitted by the pulsar, to arrive slightly later than expected when the distance between the Earth and the pulsar is stretched by the gravitational wave, cause the signal from the pulsar to arrive slightly earlier when the gravitational wave is squeezing the distance between the Earth and the pulsars. So we can see deviations in the arrival times of the signals from the pulsar compared to prediction of our models. And hopefully these deviations are large enough to allow us to detect the signal, the imprint which is left by gravitational wave passing through our galaxy. And just a few months ago, we have released the results of our most recent analysis, which shows evidence for the presence of a background of gravitational waves which is permeating the whole galaxy. So what is a background of a gravitational wave? So if we go back to the lake analogy, a single gravitational wave is the ripple on the surface of the lake, which is produced if you throw a single stone into the lake, right? A background of gravitational wave is something similar to what you would get if you throw a bunch of stones in the lake at the same time. So a background of gravitational waves is really the superposition of many gravitational waves. So it's like there is a constant hum permeating our galaxy produced by these gravitational waves. And NANOGrav is not the only experiment or collaboration seeing this signal. There are many other PTA collaborations around the world which have found a similar evidence for a background of gravitational waves permeating the whole galaxy.
Amazing! And now, why is so important to search for slowly oscillating gravitational waves? And what is your contribution?
Being able to detect such low-frequency gravitational waves will open a completely new window into our universe. So a few years back, LIGO in Virgo detected the first gravitational wave, and this is, amazing. It completely changed the way we look at the universe. However, ground-based interferometers like LIGO and Virgo can only detect a narrow band in frequency space for gravitational waves. And if you think about our experience with the exploration of the universe with electromagnetic waves, which is something we have been doing for hundreds of years, being able to detect different wavelengths of electromagnetic radiation has really allowed us to discover and study different kind of astrophysical phenomena. That's because some objects will emit dominantly into radio waves, some others into X-rays, and some other into visible radiation. So being able to detect different wavelengths of electromagnetic radiation allow us to study them all. And similarly, in this new exploration of the universe with gravitational waves, being able to detect different wavelengths, so going from the high frequencies, which are detected by LIGO and Virgo, all the way to the lowest one, which are detected by NANOGrav and other PTA collaboration, will really maximize the kind of discoveries that we can do using gravitational waves. And the role that I'm playing in this new exploration is really try to understand what could be the origin of such low-frequency gravitational waves that we are starting to see in PTA experiments. So one possibility is that these gravitational waves are produced by supermassive black holes, with masses millions or billions times the mass of our Sun. These objects are believed to live at the center of most massive galaxies, and as galaxies merge during the cosmological history, also the black holes which are at the center can meet and form a binary system. So they will start in spiraling around each other, and in these cosmic bands, they will produce a huge amount of gravitational waves at very low frequencies. So frequencies that are not detectable by LIGO and Virgo, but that we are able to detect using PVA experiments. Another possibility, however, is that these gravitational waves were produced in the early universe, so fractions of a second after the Big Bang. And detecting these primordial gravitational waves will be a watershed moment for cosmology and particle physics, as it will be the first direct message that we receive from the very early universe and could possibly allow us to understand the dynamic of the universe at such early time. So trying to discriminate between these two possible sources is taking a big chunk of my research time at the moment.
Fantastic, Dr. Mitridate. Now we are at the end of this podcast, and do you expect further developments for this latest work?
Yeah, absolutely. So we are currently keep collecting data. So we keep observing these pulsars, and we are also discovering new pulsars which are adding to our dataset. And doing so, we are really increasing our sensitivity to the signal from gravitational waves. So hopefully in the next few years, we'll be able to pinpoint the origin of this background of gravitational waves. And once we have identified the origin of the background, that's when the real fun begins, because we can start to characterize the background and study its properties. And if the background is produced by supermassive black holes, this will allow us to study and understand better how galaxies have formed and evolved over cosmic times. While if the signal is produced in the early universe, this would be amazing and could help us to transfer some of the big open problems and puzzles of cosmology and particle physics, like understanding what is dark matter, what was driving the exponential expansion of the universe at early times, or maybe understand why the universe is made mostly of matter and not of antimatter. And more in general, I think we are just starting to explore the universe using gravitational waves, and I expect many more exciting discoveries to come in the near future. So let's stay tuned.
Thank you so much, Dr. Andrea Mitridate, and thanks our listeners. If you have any questions about today's podcast, you can get in touch on Chelonia Twitter. Feel free to subscribe chelonia.swiss website and be part of the community. In meantime, stay tuned for our next interview. Thank you again.
Thank you, it was a pleasure.